Hello, my name is Benoît Sagot. I'm research director at Inria in the Almanac team, a research team dedicated mostly to natural language processing, and I'm the holder of a Prairie chair. I'll be speaking today about resources for multilingual NLP in the neural era, and I will speak in particular about the examples of OSCAR and CamemBERT. The spread of neural approaches to NLP has increased the importance of two particular types of language resources, namely, firstly, language models. As you all know, they play a crucial role in most NLP systems today. And secondly, also very important, large-scale raw text corpora on which such language models are trained. Of course, the development and publication of such language resources is therefore a crucial challenge. And I will speak today, as I just said, about two examples. Firstly, the very large multilingual raw corpus OSCAR and the French language model CamemBERT. These two resources are developed within the Almanac team at Inria Paris. Another thing that I think is really important is to be aware of some of the limitations of both types of resources I just mentioned, namely raw text corpora and language models. And this is why I will dedicate some time at the end of this talk to discuss some of these limitations. So let's start with OSCAR. As you know, we need raw text to train large-scale language models. And there are two main sources for raw text data. One type of source is non-freely accessible data. Such data is problematic for a number of reasons. One of them being that training language models on such data is not clearly legal. And this is especially the case if the data was retrieved illegally. So clearly what we want to do is to collect freely accessible data and train our language models on such data. And nowadays, most freely accessible data is to be found online. Of course, to be accessible does not necessarily mean to be redistributable, but this is the type of data we can train language models on without too big of legal problems. Now, how can we access such data? There are two main ways. You can either build your own crawler, which is a very difficult endeavor, or you can rely on the crawls provided by Common Crawl. Common Crawl is a non-profit American foundation, and they developed a crawler aimed at collecting as much data as possible on the internet. Every month or every other month, a new dump is published by Common Crawl and can be used freely. These are very large dumps with a lot of data collected on the internet. They are really big as tens of thousands of plain text files, not sorted by language, that together constitute tens of gigabytes of data. Turning a Common Crawl dump into a multilingual corpus is therefore really hard. It involves at least language classification and filtering and cleaning of these raw files. I can cite two examples of such corpora extracted from Common Crawl. One is fast text. They use a relatively computationally intensive pipeline, and the resulting corpus has not been published. And another one is CCNet. Again, the corpus has not been published. The pipeline has been published, was published in 2020. OSCAR is another example of a corpus based on Common Crawl dumps. OSCAR stands for Open Super Large Crawled Aggregated Corpus. When we developed OSCAR, our goals were threefold. Firstly, we wanted to develop an efficient processing pipeline to turn a Common Crawl dump into a multilingual corpus. Secondly, we wanted to create a corpus that we could distribute freely. And thirdly, we wanted to make it possible to train new language models on large-scale text data, thanks to this corpus. So the first version of OSCAR, which was published in 2019, used a pipeline called Go Classy, developed in Go. And the difference with the fast text pipeline, on which it is partly based, is that the fast text pipeline is synchronous. So basically, the way the common core raw data is processed is not as parallelized as it could be. And the major difference between Go Classy and the fast text pipeline is that Go Classy is asynchronous, thereby taking much more advantage of the possibilities of parallelizing the processing that is needed to classify by language and to create the output corpus. The result is called OSCAR 2019. We used it to train the French language model CamemBERT, on which I will come back a bit later. We also used OSCAR 2019 to train ELMO language models for 5 languages, which were then evaluated on 2 tasks, dependency parsing and part-of-speech tagging, reaching state-of-the-art results. We also trained an ELMO language model for French with state-of-the-art results as well on named entity recognition. OSCAR 2019 was also used by others to train several monolingual and multilingual language models. Here is a probably non-exhaustive list of languages for which models have been trained based on OSCAR 2019. And OSCAR 2019 is freely downloadable, both on the Humanum platform and via Hugging Face. There were a few limitations regarding OSCAR 2019, and especially today. The dump we used is from 2018, so basically OSCAR doesn't know about COVID-19 and is pre-Brexit. OSCAR 2019 did not include any metadata associated with the raw data. Go Classy's speed and reliability was clearly improvable, even though it was an improvement over the fast text pipeline. And we had identified a number of quality issues, although it was, to be fair, evaluated as one of the cleanest, relatively cleanest, largest scale corpora, as I shall discuss a bit later. So we developed a new processing pipeline called Engolient, and we used this new pipeline to create a new version of OSCAR called 2109, because it was created in September and published in September 2029. Engolient is much faster with, again, additional parallelization. It's also written in Rust rather than in Go. It is more modular, more parameterizable, and better documented, and it results in a approximately 2 times speed up of Go Classy. And this new version of OSCAR also includes limited metadata in the corpus. And again, we used a newer dump. To be precise, we used the August 2021 Common Crawl dump to create this new version of OSCAR. It resulted in an increase of 15% in terms of raw text volume and 15% of additional size due to metadata. So this latest version of OSCAR covers over 160 languages. It is again freely available on Humanum for research purposes via direct download, and it is also available via Hugging Face. Just to give you an order of magnitude of the size of the files that we have to handle and of the size of OSCAR, here is the beginning of the list of corpora for each language. And as you can imagine, if we have almost 200 megabytes of data for languages such as Afrikaans and Amharic, we indeed have to deal with huge data sets, huge files, and using Go or even Rust is absolutely necessary to process such large files. Otherwise, everything takes too much time. So it's a real engineering challenge to actually be able to generate such a corpus based on common crawl dumps. Now that we have OSCAR, and in particular the French subcorpus of OSCAR, we can train language models for French. And this is exactly what we did with CamemBERT. So the context in 2019 was, of course, not the same as the context that we enjoy today. Back then, contextual language models had just arrived, and most notably, we had Elmo, a handful of Elmo Elmos for languages other than English had already been published, but not many. And BERT was the new thing, and its variant Roberta a little bit later. Of course, the English BERT models already existed, the multilingual BERT as well. And in the original BERT paper, they also trained a version of BERT for simplified and traditional Chinese. There was already a German BERT, but all of these non-English BERTs were trained on limited data, apart, of course, for the original BERT. Also, XLM and XLMR multilingual models were already there. But basically, there were no monolingual large-scale model trained on large-scale data for a language other than English. And so we decided to investigate the question of whether it was an interesting thing to do to train a monolingual language model. So with CamemBERT, our goals were threefold again. We wanted to train and publish a freely available French language model on large-scale text data. We wanted, as I just mentioned, to compare multilingual versus monolingual approaches to language modeling. Is it better to train a language model specialized on French, or is it better to actually rely on multilingual language models? And we also wanted to investigate the impact of the size and of the heterogeneity of the training data on the downstream performance of the language models that we train. So what we did is we used the French subcorpus of OSCAR and trained on it a variant of Roberta, and this resulted in CamemBERT. But of course, we did some experiments with a number of training corpora of diverse sizes and heterogeneity levels. Of course, we used OSCAR, which for French consists in 135 gigabytes of data. We used CCNet, which is, as I already said, also common crawl based, but with a Wikipedia-based filtering, approximately the same size, but a little bit more homogeneous because it is meant to be not too dissimilar to Wikipedia in terms of type of text, etc., etc. And we also played with the French Wikipedia, which is only 4 gigabytes of text. In order to evaluate CamemBERT, what we did is we used 4 downstream tasks, part of speech tagging, dependency parsing, named entity recognition, and natural language inference. And in most cases, we used CamemBERT in 2 different settings to be able to compare the one with the other. One is to use CamemBERT as an embedding supplier, so as a fixed embedding supplier. And of course, the other way to use a language model such as CamemBERT is to do some fine-tuning to the specific task at hand. This is the large table of results. Basically, what you want, you don't want to read all the figures there, but what you want to learn from this table is that basically CCNet and OSCAR perform approximately as well as the other when they are of size 4 gigabytes, and they both perform much better or significantly better than Wikipedia, which is of 4 gigabytes. So what that means is that the diversity of the content in CCNet and in OSCAR makes the language model that we can train on them of better quality than the language models that we can train on Wikipedia, which is much more homogeneous in terms of style and type of sentences and type of content. And another very interesting thing is that, in fact, the language model trained on 4 gigabytes of OSCAR is virtually of the same level of quality than the one trained on the full OSCAR. And that came as a surprise. So basically what it means is that you do not necessarily need 138 gigabytes of data to train a good quality language model. 4 gigabytes might be enough, especially if it's, but it needs to be a diverse corpus, diverse in terms of genre, domain, style, etc., etc. Still, you can see on the top part of the table, which is dedicated to results obtained with fine-tuning, that there is some gain in using the complete OSCAR. It's just that the gain is not as massive as we could have expected. These two tables are extracted from the paper on CamemBERT, and they show that thanks to CamemBERT, we were able to improve the state of the art in fact, all 4 tasks that we used for downstream evaluation. And this means that we improved over baselines on the one hand, so CRF approaches to named entity recognition and so on and so forth, but also we improved over the multilingual language models. And you can see, for instance, on NLI that our CamemBERT models result in better scores than what can be reached using the multilingual BERT or variants of XLM. Now, the take-home messages regarding CamemBERT are therefore that 4 gigabytes of pre-training data is enough to reach state-of-the-art performance or almost state-of-the-art performance, provided that the data is diverse, as opposed to Wikipedia, and that a monolingual language model such as CamemBERT performs better than a multilingual model such as MBERT or XLMR. Now that I have discussed a little bit on OSCAR and CamemBERT, as I said in the introduction, I think it's important to discuss a few issues regarding quality problems and problems related to bias in language models. Now, we have taken part in a large-scale investigation of the quality of large-scale corpora, published in a workshop last year, and that will be published in Takehome next year, that involved comparing and studying 5 large-scale corpora, 3 of them parallel, so dedicated to training machine translation systems, CC-aligned, Paracrawl, Wikimetrics, and 2 monolingual, OSCAR and MC4, multilingual C4. As you can see, OSCAR has more languages, it covers more languages than any other of these corpora, and you will see that this might have an impact on some of the results obtained. This is a graph that shows you the fraction of languages in each data set that is below a given quality threshold. So the quality threshold here is defined as the percentage of sentences that are classified, that are correctly classified in terms of language classification. And this was evaluated on random samples by humans. And as you can see, unsurprisingly, those corpora that include fewer languages only include acceptably well-resourced languages, and therefore display good performance very early on. Look at Paracrawl, for instance. But as you can see, OSCAR behaves quite well and ends up having a very good performance. And in fact, it turns out that OSCAR is not that bad at all, indeed, in terms of quality. So the take-home messages from this study are, there are quite a few, but some of them are that CC-aligned and Wikimetrics have severe quality issues. Non-linguistic content is a more common issue than wrong language content. So actually, language classification is a problem, but identifying content that is not linguistic is also a problem. OSCAR behaves particularly well in these regards. That was good news for us. Another take-home message is that low-resource datasets tend to have lower quality. So basically, those languages for which we do not have a lot of data, well, it turns out the little data that you have is generally of low quality with a lot of language classification errors. The situation for mid-resource languages is unclear, and the situation for high-resource languages is better, at least for corpora other than CC-aligned. Now, another surprise, if I might say so, is that offensive content is relatively rare, and even pornographic content is, I should probably not have written acceptably infrequent, but it was less frequent than what we feared, at least in most corpora. And also, we realized that there were several issues with language codes. Standardization of language codes is still a problem when it comes to taking that into account in real life. Now, these quality issues have a potential impact on everything that we do. First of all, if you have quality issues in the text corpora that you use to train your models, you might end up with low quality in downstream applications. Of course, for instance, training corpus quality and machine translation quality do correlate, and that is shown in the paper. Another problem is what is called in the paper representation washing. So basically, if low quality data sets are used as benchmarks, they may exaggerate, overestimate, or indeed underestimate model performance with many possible unwanted results. For instance, you might believe that you have solved a problem for a low resource language, but in fact, no. In fact, it's just the quality of the data sets that results in artificially overestimated performance metrics. And a third type of potential impact is what is called in the paper trust in incorrect facts. So that is especially true for machine translation, but also for text generation. For instance, models might predict incorrect translations or other outputs as the result of the training data being of poor quality, and people might then take what the model has generated for granted. If you machine translate a text in Chinese and you don't speak Chinese, and the output involves the name of a city, for instance, or a date, and it's not the correct city and not the correct date, you might trust the output, and with no easy way of understanding that, in fact, it's not the right city, not the right date in the output. So these are problems in terms of quality of language classification, filtering, alignment for parallel corpora. But the thing is, even if they were perfect, even if language classification was perfect, filtering was perfect, and alignment was perfect, the very content of the text in the data sets can have a negative downstream impact. And this is what I would like to discuss now. Because indeed, this results in biases in language models. As you all know, current language models are obviously trained on huge data sets such as OSCAR, and this comes with representativity biases. And I will come back to this in a minute. Of course, there are many other challenges, one of them being that the computational cost, and therefore energetic cost, and therefore ecological cost are huge, and they tend to increase. Plus, there are disparities between the private sector and the public sector, between countries, and so on and so forth, regarding the accessibility of such resources. But training language models on huge data sets also means that these language models, as the data sets they are trained on, will reflect the way people who wrote these texts in the data sets perceive the world, write about this world, and write in this world in the context where they live. And this results in representation biases, on which I will say a few words as well. Of course, a number of studies have already been published on this topic, and here are just a few of them. In order to discuss, I'd like to discuss these representation and biases, I would like to say a few words about encoders versus decoders, and you will see why. As you probably know, there are three main types of neural language models based on the encoder and or decoder parts of a seek-to-seek, for instance, transformer architecture. Right. So some language models are based on the transformer encoder, for instance, if they are based on a transformer. And this is the case of BERT, Roberta, and others. And the task in which they are trained is to guess a masked word is in sentence. There are language models based on a transformer decoder. And this is the case of the GPT family, for instance, such as, or for instance, GPT-3. And in such cases, language models are trained to continue a sentence or a text based on the beginning of a sentence or a text called the prompt. And these are so-called generative language models. And in fact, these language models are the most convenient language models to investigate bias-related issues. And this is why I wanted to say these few words on them. And then, of course, there are language models based on full transformer architectures that involve the encoder and the decoder. Now that we have to say that, let's go back to representation biases and representativity biases. So let's start with the representativity biases, and in particular, biases related to multilinguality. OSCAR and most other large-scale raw corpora are extracted from the web, as we discussed earlier on. But the thing is, for most languages on the planet, which are called low-resource languages, there is little data, if any, on the web. And moreover, it's hard to identify this data, as discussed earlier on. And this results in issues with multilingual language models. Firstly, multiple scripts are represented in multilingual language models, and these scripts might have very diverse distributional properties, which create biases. Indeed, some scripts are used by multiple languages, thereby creating a shared vocabulary which benefits. So these the languages involved benefit from one another, which create bias. Languages with structural similarities are mutually beneficial. This is one of the bases of transfer learning between structures in such models, and this also creates biases. And of course, as you probably know, high resource languages are not very representative of the diversity of languages on the planet. Most of them have low morphological complexity and relatively fixed word order. And because they are highly represented, this also creates a bias. Another issue related to representativity is that of language variation. In fact, even for well-covered languages, representativity is not optimal, to say the least. Again, data sets are often extracted from the web, and when it's not from the web, it's often from books. And the web or books are hardly representative of what a language is in any possible sense of that sentence. For instance, content producers on the web are certainly not representative. An example is that Reddit users are often men, 67% of them are men, and 64% are between 18 and 19 years of age. It's not 18 and 19, there is an error on my slides, probably 18 and 29 years of age, but still. And of course, marginal communities and marginal opinions are underrepresented. I'd like to switch from representativity biases to representation biases and take the example of GPT-3, which I mentioned earlier on, one of these generative language models that received a lot of attention, even in in large audience media. Let's take the example to start of gender bias. So the idea of how you can identify bias in GPT-3 is you give it a prompt and you see how it reacts and you study its answers. So if you, for instance, use the prompt then you insert an occupation was A, GPT-3 is then asked to predict the next word. And with 388 occupations, Brown et al. In 2020 investigated whether the next word was predicted to be man or women. And they found that in 83% of cases, man was predicted. Another example was if the prompt is he was very versus she was very, or he would be described as versus she would be described as, you can see which adjectives are predicted after he versus after she. And as you can see in the table below, the adjectives predicted for men are not at all of the same nature of those predicted for women. And this also displays a bias which is not inherent to the language model in itself. It's just that the language model has been trained to reproduce these biases as they are found in the training data. This is another example of representation bias, this time related to ethnicity. So prompts such as the ethnicity man was very something, that predicts an adjective, and they investigated whether these adjectives were positive or negative. And as you can see, depending on the race in the American sense of the term, the sentiment score associated, so positivity or negativity associated with the adjective, is not the same. And that is so even with very large models. Another example, based on religion, they tried to prompt religion practitioners are, and they analyzed the continuation, so how GPT-3 predicted that the sentence should end. And as you can see, the most favored descriptive words for the different religions are not at all the same, and they reproduce the biases as can be found in the training data. Now, which attitude can we adopt given these observations? Firstly, obviously, quality in the raw text corpora can be improved. And indeed, we are working right now to improve language classification and non-language detection in OSCAR. But regarding biases, there are actually two possible attitudes, an a priori attitude and an a posteriori attitude. As far as corpora is concerned, the a priori attitude consists in detecting and removing unwanted content, racist content, violent content, and so on, offensive content. The a posteriori attitude consists in detecting and tagging such content, but not removing it. In language models, the a priori attitude consists in representing each bias, for instance, with a scalar that needs to be minimized, and try to remove the bias from the language models in that way. And a posteriori attitude would be to try and live with it, dealing with these biases in a post-processing step. And indeed, the question is, what can we do? What should we remove if we want to remove stuff? And in fact, should anything be done at all? And in fact, this depends, I think, on whether you want to, you have in mind analysis or generation as an applicative goal. Because if you want to be able to analyze biased content, maybe it's important that you have bias in your models. If you want to generate data, maybe you don't want what you generate to be biased. But in fact, trying to remove biases in a language model means to make the language model more objective. But what is objectivity? In fact, to decide that a point of view is objective is a subjective decision, which is influenced by a number of factors. And this very decision disembodies, as the term is by Wassim et al. 2021, this very decision disembodies the supposedly objective point of view, which has the result of disconnecting it from its subjectivity, thereby giving it the appearance of universality. And this is bad because it means that the subjective decision of removing this or that bias will be presented as a universally objective decision, which it is not. I will not read the quote by Wassim et al. 2021 now, but I recommend you to read the whole paper. As a conclusion, there are a few things that can be said. Firstly, very large raw text corpora and large language models, of course, play crucial roles in current NLP. And extracting such corpora and training very large language models on these corpora raise multiple challenges, including and not limited to computational costs. It's not necessarily accessible to everyone, to say the least, and it comes with energetic and therefore environmental costs. Representativity biases, as we have seen, underrepresented languages, domains, genres, styles, registers are a problem. And the fact that they're underrepresented is comes generally with the fact that they are often poorly represented with a lower quality. Then there are representation biases, gender bias, ethnicity bias, religion bias, and a number of other ones. But the question of should we remove these biases is a difficult question to answer. It's not necessarily the case that we want to do it. And if we do, it's hard to do it and hard to understand how we want to do it. And finally, there are the issues related to explainability and transparency, because indeed, no guarantee can be provided that such language models, especially generative language models, do not produce factually incorrect and or unacceptable outputs. So these are some of the challenges faced by current language resources, both large-scale data sets and language models. I would like to conclude by stating the importance and impact of developing these resources in a way that allows for a free redistribution. I think it's very important that such endeavors are shared with others, and that the resources that we build, especially when they're hard to build and computationally intensive to build, should be shared freely. And this is what we are trying to do with OSCAR and CamemBERT and other language models we have been involved in the training of. Thank you very much.